The mystery of imaginary number, the gateway to higher dimensions.
Hey, my name is Dom. Today I'll guide you to reveal the mysteries of imaginary numbers. This number is a gateway to the fourth and higher dimensions. Numbers emerged alongside the development of language, with each nation developing its own language and number system. Despite this diversity, all number systems share a common foundation, the base 10 system. This universal base stems from the fact that humans have 10 fingers, which likely influenced the creation of counting systems around the world. When humans know how to add and subtract numbers, then the minus numbers and 0 are added to fulfill the number system. For example, 1 plus 2 equal to 3. 3 minus 5 equal to minus 2. 4 minus 4 equal to 0. When humans know how to multiply and divide numbers, then the fraction and decimal numbers are added. 3 multiplied by 2 equal to 6. 1 divided by 2 equal to 0.5. 1 divided by 7 equal to 0.1 for 2857. When humans start to occupy lands, they have to use a square as a unit to measure the area. They know how to power and take root of numbers, then the irrational numbers are added. 3 raised to the second power equal to 9. Square root of 2 equal to 1.414. Pi is equal to 3.14159 to 6. The problem comes with the question, why do the minus number multiply with the minus number become a positive number? We'll start proofing by let minus 3 multiply by minus 3. We can add 9 and minus 9 to the expression, so the result will be the same. Minus 9 is the result of minus 3 multiplied by 3. Minus 3 is a common factor. We can move it out of the blanket. Minus 3 combined with 3 becomes 0. Minus 3 multiplied by 0 is 0. So this to prove that minus 3 multiplied by minus 3 become positive 9. With the proof of minus number multiplied by minus number become positive number. That means the square of minus number become positive. We also know that square of positive number become positive, and the square of 0 is 0, leading to the fact that the square of every real number is positive number. With the knowledge of algebra and geometry, a graph of a parabola function is drawn. From this graph, y is the value of function x squared, then y is always positive. The minimum value of y is 0, no value of y is less than 0. We can write the equation in the form of function where x is the domain or independent variable. Y is the value of the function or range or dependent variable. If we have y as a function of x equal to x squared, then we can write x as another function of y equal to square root of y. Square root is a new function called inverse function. The graph of inverse function or square root function can be drawn. The shape is a parabola, but in different direction. X is called the independent variable, means that we can choose any value of x. Y is called the dependent variable, means that the value of y depend on the chosen value of x. In the graph, if we choose x equals to 4, by drawing the vertical line x equals to 4, the vertical line cut the upper curve at y equals to 2. We also can draw the vertical line downward to cut the lower curve at y equals to minus 2. That means one value of x associated with two values of y. By the definition of function, we can have only one value of dependent variable y. To make the relation to be function, we divide the graph into two curves. The upper curve is function square root of x, while the lower curve is function minus square root of x. From the graph, the domain or the independent variable or the values of x are restricted to be greater than or equal to 0? In this area, we can find the values of function or the values of y. If we try to find the value of function on the left side of the graph by writing y equals to square root of minus x, we could find no value of y associated. We might say it's impossible to take the square root of minus number. For solving the quadratic equation, mathematician found the solution as shown in the formula. If the term inside the square root is less than 0 or b squared is less than 4c, the solution of the equation would contain the square root of negative number, which is the impossible solution. Why so many impossible solutions from the quadratic equation? Or the mathematic try to tell us something? Let's start with this simple equation. X squared plus 1 equals to 0. Then x squared equals to minus 1. Finally, we get x equals to plus and minus square root of minus 1, which have no place in our numbering system. Mathematicians think that there should be a new number system. We could not find this number system in the real world, so they named it the imaginary number and give the symbol I. We define I as a unit of imaginary numbers. Then the imaginary number shall be multiple of I, such as 2i square root of 2 multiplied by 1, and so on. Imaginary numbers have no place in the real number system. They have their own space called imaginary dimension. We are reaching the gate of imaginary dimension. Come with me to explore the world of imaginary numbers. Real numbers are the ruler of our real-world dimensions.
Imaginary numbers are the ruler of imaginary dimension.
Let's start with the simple function y equals to x squared. The shape of this equation is a parabola.
What is the shape of this function in the imaginary world?
Let's explore the imaginary world by let x be an imaginary number and find the value of x squared.
The shape of this function in the imaginary world is also a parabola function but upside down.
These are graphs of the same equation, but shown in different dimension. If we combine these two graphs, the result will look like this. In the graph, we let imaginary axis perpendicular to the x-axis, y. In the graph, the curves are only above the real x-axis and under the imaginary axis. There should be some value of y in other area. To find the value of y over the whole area, we must define the domain of the function as the combination of the real part and the imaginary part of x. So x is defined as complex number and the plane become a complex plane. Let's x be a complex number. We can write x as a combination of real part and imaginary part. X can be plotted in a complex plane with real axis and imaginary axis. Let y be a function of x. If x is complex number, then y is called a complex function. For the square function, we can substitute x as a combination of real part and imaginary part. Erase the term to the second power, separate the real part and the imaginary part. The final result shall be as shown. After rearranging the function, we can separate the real part and the imaginary part. If y composes of real part and imaginary part, then y become complex number. If y is a complex number, then we can write y equals to c plus di, where c is the real part and d is the imaginary part. Compared with the above equation, the real part c equals to a square minus b squared and d equals to 2 multiplied by ab. Now we have a function of complex variables with a and b are independent variable or domain. C and d are range or dependent variables. We can calculate the value of c from the formula and the value of d from the formula. The domain of this function has 2 dimensions. The range of this function also has 2 dimensions. So we need for coordinates to specify a point. Then this function is a 4-dimensional function. The shape of the graph would be 4-dimensional surface which is beyond our imagination.
Let's explore our three-dimensional world. The three-dimensional object have three projections. The projection of the object on the right wall is a triangle. The projection of the object on the left wall is a rectangle. The projection of the object on the floor is a circle. These projections are from the same object.
The three-dimensional object have three projections on two dimensions plane. On the right wall, x is 0 or constant. On the left wall, y is 0 or constant. On the floor, z is 0 or constant.
For the four-dimensional object, there are four projections. Each projection has three dimensions.
Our real world is one projection of the four-dimensional world.
By using the spreadsheet, we can calculate the values of the function as accurate as we require. There are four columns in the sheet. Each column represents a dimension. A and B are independent variables. That means we can set any value as we want. C and D are dependent variables, which are calculated from A and B. The data in the sheet represent a four-dimensional object, which is beyond our imagination. We cannot plot graph of all four dimensions together. If we let one of the four dimensions to be 0, the remaining three dimensions can be plotted as a 3D graph. If we let the fourth column to be 0, the remaining first three columns become a 3 dimensions graph. Fortunately, we can view this shape by using a program called Geogebra. We use the relation c equal to a square minus b square to calculate the third dimension. In Geogebra, we need the function in the form of x and y. The relation can be written as function of x and y equal to x square minus y square. Search for the word Geogebra and then click on geogebra.org. The first interface of Geogebra shows 2D graphing. Change to 3D by click the graphing drop-down and then select 3D graphing. Write the function in the input panel. Geogebra is a powerful tool. It's very fast to produce a nice picture. Once we finish typing, the graph is already created. We can use the screen keyboard to write mathematical formula such as the exponent and square root. Once we finish writing the formula, the final picture of the complex function appears. Click X to close the screen keyboard. To see larger image, we can click on the picture and drag to see different view. If we drag it fast enough, it will rotate. Let's try. This 3D graph is created from the table, which x is the first dimension and its real number axis. Y is the second dimension and its imaginary axis. Z is the third dimension and its real part of the value of the function. This 3D graph is created from the table, which is a 4D object, by let one of the four dimensions to be 0. The 3D graph is called the projection of the 4D object. We can let any dimension to be 0, so we can have four projections from the same 4D object. This 3D graph is the first projection of the 4D object that will start explore its properties. Starting by setting the imaginary axis to be 0, or let y equal to 0, then the projection of the 3D graph will be on the xz plane. We just type the plane equation y equal to 0 into the input box. The plane appears in the graph. If we want to see the intersection curve line on the plane, click on the Tools button. Click at intersection line between two surfaces. Click on the first surface and then click on the second surface. Then the intersection curve line appears. Click on the Algebra button to see the equation of intersection line. Geogebra shows the intersecting equation x squared minus z equal to 0. We can rewrite the equation to z equal to x squared, which is the parabola curve as our original equation. We can examine the function. If y equal to 0, then the function remain x squared, which is also a parabola shape. We can hide the complex surface by click at the circular button. the complex surface disappear. Remain the projection that we can see from our real world. We can create the plane that y equal to any constant. Let write y equal to a and press enter. A plane y equal to 1 is created. Geogebra make a as a parameter, ranged from -5 to 5. Click the button play. From the function, we can write z equal to x squared minus y squared. From the plane equation, y equal to a. We can replace bi with a, change it to GeoGebra form, x squared minus a squared minus z equal to 0. Write the equation in the input box and enter. Click the play button. The plane moves along the y-axis, causing the intersection parabola curve on it, which is the projection of the invisible complex surface. Show the complex surface by click on the circular button. Then click on the play button to see the moving plane cut the complex surface.
Now, we can find the intersection of the complex surface by using a plane y equal to 0 or any constant. The shape of the projection or intersecting curve is a parabola. If we cut the complex surface by the plane x equals to 0 or equal to any constant, what the shape of the projection or the intersection would be. Let's create a plane x equals to 0 by typing the equation in the input box. Then the plane appear. We can see the intersection curve line equation by click on the Tools button and then click the intersection between two surfaces. Click on the plane and the complex surface. The intersection curve line appear. Click the Algebra button to see the intersection equation. The projection or intersection is also a parabola curve, but upside down. If we want to see the intersection of the plane x equal to any constant b, we are to change the form of the function to z and substitute x by b. Rewrite the equation in the form of GeoGebra format. Click the screen keyboard button to write the equation in the input box. We also write the plane equation for intersection. The intersecting curve appear. We also need to show the plane. Write the plane equation x equal to b in the input box. Click play button to see the moving intersecting curve. We have seen the projections on the plane x and y equals to 0 or constant. Now let's see what projection would look like if we create the plane z equals to 0. Write the equation z equals to 0 in the input box. The plane z equals to 0 appear, but it is the same plane as provided by GeoGebra. We'll hide one by click at the gear button. Uncheck the show floor plane. We can see the intersection of the complex surface and the floor by click the Tools button. Click intersection between two surfaces. Click at the complex plane and click on the floor. The intersection lines appear. Click at the button Algebra. Surprise! The intersections are two straight lines. Let's rotate the graph. We can create the plane z equal to c. Let's substitute Z by C and rearrange the equation. Type the equation in the input box. The intersection lines appear at the plane Z equals to 1, which C is a parameter. For easily see the intersection curve, type the plane equation Z equals to C in the input box. The plane appear ready for moving. Click to hide the floor plane and click play. The equation of the intersection curve between the complex surface and the z-plane is a hyperbola curve, while the intersections in others planes are parabola. So this 3D shape is called hyperbolic paraboloid. Let's see the animation from top view. Now, we complete exploring the properties of the first 3D object. Draw the 3D and 2D projections with the associated equations. We are to examine the second, the third, and the fourth object. Draw all projections and fill in the blank area. Let's step up to the second object. Let's look back to the square function. We've already drawn the 3D graph of the real value function. Now, we will proceed on the imaginary part. We can draw the graph by let the third dimension to be 0. Write the function f equals to 2xy in the input box. The complex surface appear. We want to see the projection of the complex surface on the plane x equals to 0. Write the plane equation x equals to 0 in the input box. We can find the intersection curve line by click the Tools button. Click the intersection of two surfaces. Click on the complex surface and the plane. The intersection line appear. Surprisingly, it's a straight line. Click at the Algebra button to see the equation. We can create an intersection curve line at x equal to any constant a. From the function, we replace the function with z and replace x by a, rearrange the equation. Add the plane equation and write the equation in the input box. In order to see the intersecting plane, we also write the equation x equal to a in the input box. Close the plane x equal to 0 and then click play button. The intersecting lines are very strange. It's a series of straight lines cutting and rotating around the x-axis. It also very nice. We can use the same method mentioned before to find the intersection line created by the plane y equals to any constant b. We also can find the intersection line created by the plane z equals to any constant c. We got the same hyperbola curve, but the axis is rotated by 45 degrees. We can combine all of the intersection lines. It look very interesting. The shape of the complex surface look like the shape of hyperbolic paraboloid. The intersection curve has only hyperbola curve. Y has no parabola curve. Let's rotate the vertical intersecting plane around the z-axis by any degree a, or write the plane equation in the input box. The vertical plane appear. Click play to start rotation. Write two intersecting surface equations in the input box. Click play to start rotation. The parabola curve vary between concave and convex curve. Very nice. Now we know the condition in the first dimension x equal to a can cause an intersecting line with the complex surface. The condition in the second dimension y equal to b can cause an intersecting line with the complex surface. The condition in the fourth dimension z equal to d can cause an intersecting line with the complex surface. We jump over the condition in the third dimension, which is invisible from this graph. The condition in the third dimension is x squared minus y squared equal to c. If c is a parameter, what shape of the intersecting curved line with the complex surface? Unfortunately, Geogebra could not find the intersection of these two surfaces. However, we can draw these two graphs separately. Let's see the intersecting curved line. We are now halfway of the exploration. We know the first and second 3D projections and the associated 2D projections. Let's explore the third 3D object. Let's consider the third object. We can write the equation as follow. From the table, b is invisible. We are to eliminate b from the equation. Let b equal to d divided by 2a. Substitute b in the first equation. We get the equation without b as follow. We'll examine the properties of this equation. Change the variable in the form of GeoGebra and write it in the input box. We get the graph of the third object. Create the plane x equals to c, intersect with the complex surface by substitute x with c. We get the intersecting curved line. Create the plane y equals to c, intersect with the complex surface by substitute y with c. We get the intersecting curve line. Create the plane ZAD equals to C, intersect with the complex surface by substitute ZAD with C. We get the intersecting curve line. Now we know the shape of the third 3D projection and the associated 2D projection images. We fill in the pictures. Let's explore the fourth and the last projection. From the table, we can write the equations. In this table, we hide the force dimension, so we will eliminate A from the equations. We rearrange the equation and substitute A in the first equation. We get the equation without A and can be plotted in the 3D graph. Rearrange the equation in GeoGebra format and write in the input box. We get the 3D graph. We'll cut the surface with the plane x equal to A. Substitute x in the equation with A. Write the equation in the input box. We get the intersecting curve line. We'll cut the surface with the plane y equal to the parameter A. Substitute y in the equation with A. Write the equation in the input box. We get the intersecting curve line. We'll cut the surface with the plane z equal to the parameter A. Substitute z in the equation with A. Write the equation in the input box. We get the intersecting curve line. Finally, we can fill all the blank space. We have 4 3D projections and 12 2D projections, which are the projections of the same 4D object.
Thanks Dom to help me to present this topic. Now we know the properties of 4D object of the square function which is invisible. We can see only its projections. The 4D object has 4 3D projections depend on which dimension the viewer stay. Each 3D object also has 3 2D projections. Totally there are 12 2D projections. Next time we will examine the properties of others' function, especially the exponential function and its derivative, which is the key point to explore and understand the behavior of electromagnetism and quantum physics. Follow me.